those two descriptions of target systems. And this notion is often attributed to McMullen that I mentioned earlier. And often it's framed as the need to add back all the properties or details previously neglected by idealized models. For instance, by using some analytic method, for instance, showing that you can take the limit of some parameter and show that as the parameter varies, you end up with some limit property, and that limit property somehow is the idealized version, and we can show how it approximates more realistic property. I'll talk a lot more about this later. Right, the idea is that people have criticized this idea a lot because they say it rests on suspicious confidence that we can successfully remove all our idealizations, all the falsehoods and distortions this way. Right? And then they say we need to recover the true, for this to work, we need to recover the full representation or the true description of the world. But the worry is that if we need proofs to check idealizations, this is not what scientists do in most cases when they appeal to de-idealization, when they use idealization. And I talked about it just, right? So I think, or we think, and I think many people in philosophy of science nowadays think that de-idealization via truth or some full representation hinges on a strong, highly idealized philosopher's construct of de-idealization. And we might have reasons to worry about this based on recent works in philosophy of science, philosophy of physics, naturalized metaphysics. For instance, the idea that we only have effective theories which are not fundamental, and we know that they break down, and we have nothing else to say beyond certain limits. And we don't have that fundamental theory, right? The one that we know to be true for sure. So we can talk, people talk about this, for instance, in Porter Williams's 2019 about effective theory, effective realism. David Wallace had talked about this as well in 2022. Kerry McKenzie is working on a bunch of papers on effective metaphysics. And the question is our point is that the failure of this very specific idealized notion of de-idealization should not be taken to mean the failure of de-idealization simplicity. As many in the literature, for instance, Dokulich 2011, Nicola and Morgan 2019, Koshniks, and others seem to apply. So in the rest of the talk, I will try to use examples from physics to provide a novel, what we think is novel, but who knows, right? We provide a account of idealization and de-idealization in terms of what we call generalized asymptotic reasoning, which tries to jettison the idea that we can have a full reversal, removing all distortions, yet retaining the idea that there is still some holy connection between the model and the world. So in some sense, it's pushing back on the trend that we see in the literature today. So for us, we see the heart of asymptotic reasoning to be the search for and demonstration of convergence of idealized model to target systems, the aforementioned notion of closing in. And the question is, how do you cash that out? Right? Often, in the most formal ways, people have tried to cash it out in terms of limits in mathematical sense. Right? One specific way of showing how such models close in on the wall is to, again, I mentioned, introduce some parameter and say, as I tweak this parameter from realistic to unrealistic values, then the realistic model closes in, gets closer and closer, approximates the idealized value. So to better understand asymptotic reasoning and how we can sort of get from this mathematical notion to something a bit more general like convergence, and how that relates to idealization and approximation, I'm just going to start from a brief tour of the orthodox understanding of these concepts. example, there's this thing called the Airy equation. Don't have to worry about the details too much. But essentially, this can be used to approximate the Schrodinger equation in quantum mechanics in some ways. But the problem is that the function itself, the solution, is an extremely messy one. I'm not going to try to write down. But the asymptotic extension that, or rather, there exists this function that looks like this, which is a lot nicer. It's still kind of messy, but it's a lot nicer than this one. And it can be shown that if you take x to infinity, these two become equivalent, right? So in the limit, at the limit, they are equivalent to each other, the asymptotic solution and the general solution. But that's not true when x is far away, and the further x gets from infinity, the more they diverge and they do not equate to each other. Paradigm instances of asymptotic reasoning. And from this, we can try to extract a notion of asymptotic reasoning, which we call in our paper orthodox asymptotic reasoning. In a very formal sense, asymptotic reasoning involves simplifying a system to extract analytic patterns of its critical behaviors within some limiting regime of validity. Like, for example, here we would say close to infinity or far away from infinity, depending on our background notion of what that means. And then such patterns are obtained when we assume that some parameter, say x, can be set to approach or close in on some limit value. Infinity, 0, or whatever infinitesimal value, or any value that we think is useful in whatever context we're saying. Right? at the end, so to speak. And then we investigate exact solutions and the properties of the system at the limit. But no, we try to represent a real system with a distorted model. Now we have to ask, okay, but why are we justified to use this model, right? We simply provide reasons for using the limit system to represent a real target system. And in the context of OAR, idealizations can only be applied justifiably to represent a target system if and only there exists this kind of a limit system that something asymptotically converges to a sequence of more realistic model. The worry is that sometimes we might not be able to go 1, 2, 3 infinity, as George Gamow says. We might encounter blowups, right? So as you take the limit, you might see that there is a singularity before you get to what you want to describe, and then you can no longer use that method. So this doesn't always work, right? So it's not like, oh, it's just math and everything. It is just math, but there are some problems along the way that might not let you get from here to here. So we have to give reasons for why we are allowed to use the model. So based on what we just said, I think if we take approximation and idealizations as two facets of an underlying methodology, we can see it as two sides of asymptotic reasoning. And asymptotic reasoning is a search for convergence of models to target systems. On the one hand, approximation provides a convergence and provides justification for the use of the model by seeing how it converges. Idealization strategically targets certain regimes or looks for regimes where this convergence would be attempted to be established, enabling investigation of the system's behavior within those domains. So if we take this view, it suggests that every justified idealization should come with some kind of formal approximation scheme on the picture of OAR, which we are not taking on board, right? We're just saying, if you buy OAR, this seems to be what's going on here. Was thought to be a great foundation for quantum field theory, which is called like a renormalization group method. It's just a kind of approximation scheme. Only came about in the 80s, but that's like 20 years after, 20, 30 years after the foundation of the theory. The question then is like, well, why would they justify to use it and like represent systems with it before we have this formal scheme, right? So we think that the requirement to justify idealizations must satisfy IAR amounts to an idealization in itself. And we think that to find a broader, less restrictive account of asymptotic reasoning, we have to de-idealize the IAR and the idealization itself. So use these models that were widely available, in fact, used to build things and so on. Why would they justify to do so? So that's one worry. Another worry is that Galilean de-idealization is not in line with scientific practice. This is a line pushed by Nicola and Morgan in 2019. So they make this claim that it's an insidious presumption by philosophers of science that scientists originally start from considering the real world, i.e. the full representation, and then arrive at their models through idealizing and extracting, which led philosophers to think that scientists can easily reverse the modeling recipe to get back down to the more fully blown situation they started with, broad though that process might be, and that's what they try to show in the paper, that many idealizations, in fact, are not easily reversed. That's why the paper is called No Easy Reversal. Idealization or even on controlling their influence. And instead, we just use models for certain pragmatic goals, and then those are what decides which scientists use what idealizations and so on. So she has two claims here. One is that idealizations cannot easily be removed, and that scientists like it that way, right? So de-idealization is not taken to be a goal. Especially when these idealizations best facilitate the representation of a core causal influence and so on. Secondly, she makes a claim that idealizations are in fact unchecked. So there's little emphasis in practice for scientists to control the influence of these idealizations. And honestly, every time I read this, I'm confused as to whether it's a descriptive claim or a normative claim. It's not entirely clear, but I'll take it as kind of both, right? I think that's the implication of the book. Models containing falsehood to model the world and to such great success in many cases. We still need something like a tether between our idealizations and our world, to quote something from Catherine Eugene, right? So an account of de-idealization should provide exactly such a story for why some models are fictions, completely not about the world in some sense, while others tells us something about our world. So I think we need a de-idealized account of de-idealization. Model is. So de-idealization then can effectively justify, even if only within some assumed regime of validity and not fulfilled. So on a de-idealized view of de-idealization, we believe that there's no expectation of that full notion of de-idealization before we can begin to take models to be justified to some extent. So to some extent, it's probably doing quite a bit of work there. Procedures, demonstrating convergence within some regime of validity. So the question is, what sort of de-idealization procedures are we thinking about? If it's just Galilean, then we run back to the same problem, right? But if it's something more, then we can have begin to have a discussion about what it takes to justify models that isn't just constrained to this old debate about someone from the 1980s, right? So we try to do better by looking at scientific practice in physics, and we provide a general scheme for de-idealization procedures, and then we provide 3 ways of concretizing a schema and what follows. We don't claim that this is exhaustive. We're just saying these are the 3 we have found, and we can look further after that if we're interested. Do we de-idealize? Then we have a de-idealizing construct, which I'll say a bit more about, with which the idealized model is de-idealized. Then we have the target system, with respect to which the idealized model is de-idealized. Then we have 2 standards here, 2 normative standards, which are I don't believe you can really pin them down in any precise way, right? Depending on the context. For instance, the standard according to which the de-idealizing construct converges enough with the idealizing model with respect to relevant properties of the idealized model in a stable way. So this tells you what it means to be close enough to some idealized model. And you need another standard according to which the de-idealizing construct is considered a realistic or more realistic description of the target system, where it doesn't mean full representation in the sense of completely describing every single detail of the target system without error, ambiguity, or falsehood. That's not what we're thinking about. But we're thinking something like a more realistic model. zero value, right? If it's zero, you just get the old ideal gas equation. But if it's A and B in other values, then we can see how it behaves as A and B varies, right? Approaching zero, moving away from zero, and so on. And it turns out that when P is low and P is high, the pressure is low, temperature is high, we find that this equation approximates the ideal gas formula. And when it's far away, it doesn't. So by doing so, we find out when exactly are we happy to use the ideal gas formula when we can say we have low pressure, high temperature, where these parameters are worked out. And then we can justifiably use ideal gas model when we have this kind of situations. And that lets us de-idealize the ideal gas model because now we can understand ideal gas model as an approximation, an approximate description of a more realistic model, the area model, for instance. The fullest sense. Specifically, it doesn't capture fluid or solid behavior, right? Nonetheless, it's more realistic because it doesn't assume, at least it doesn't assume as many falsehoods, and can play the role of de-idealizing construct. It is qualitatively accurate in certain regimes. For instance, to describe the idea that there could be liquid vapor transitions. That's something that you don't get in PD equals nRT. The P and V just vary linearly, and there's nothing else. But here you get this kind of a pattern in the phase transition curve that tells you that there is a liquid vapor phase transition, like liquid transitioning to vapor. These are things that are qualitatively described by the van der Waals equation, and it's more realistic in that sense. And it's also more quantitatively accurate, even if they're both inaccurate, than the ideal gas in predicting pressure temperature. Very complicated way. It could block straightforward parameter variation that we thought of. In thinking about cosmological constant or like the thing that represents dark energy, if you try to vary and try to make it go to zero, you might think, oh, it approximates flat space time, right? But you get a discontinuity in energy if you just try to do it naively and then breaks down. Like you don't get to see the approximation because of the blow up that I mentioned earlier on. So also certain idealizations, for instance, the idea that black holes have certain nice symmetries like being time translation invariant, may not be mapped onto a nice parameter to remove. I have a recent paper on this that just got published in EJPS about how black hole evaporation requires certain symmetry assumptions that cannot be easily de-idealized in this kind of intra-model way. And that's kind of what brought me to think more about other ways that we can de-idealize. So I'm sort of like getting narrowed out on the old argument I made. When we don't have an intra-model procedure at hand, scientists instead use multiple independent modeling techniques to address the same phenomenon. For instance, they might employ what's called intermodeling, right? You use two or more distinct models, families, or methods instead of thinking about it in terms of one family and one parameter that you vary. You're thinking of different kind of equations, different kinds of models, each with their own assumptions and idealizations, and you're trying to use them to converge on one target phenomenon. For instance, a simple one, you can use X-ray crystallography, or you can use this kind of visualizing techniques for the same protein structure. And you're using completely different methods, but you're seeing roughly the same thing. You can find a way to explain why they are the same thing or they are representing the same thing. Then we have this kind of robustness argument going on. So to de-idealize a particular family of models over which we may not have intra-model de-idealization, we might try to appeal to other families of models we use as well, even if we cannot control one parameter that lets them all converge into one thing. So these models may be from the same underlying domain, in which case maybe we have some more general theory in which these models take place, or there might be some distinct model, distinct domain, in which case it gets a lot trickier. So to de-idealize some idealized model using some other models in the same domain, here's what we propose, right? You can try to search for a good enough, so this is where the good enough convergence comes in, good enough conceptual continuity for that feature, right? You identify certain features in the initial model, idealized model, and then see if that feature persists in some way that is recognizable under different modeling approaches. And then as you do that, you're refining it, and those new other models may be considered more realistic. Right? And integrating across it leads to this more realistic description of the original feature. And it shows how the original feature closes in on more realistic refinements of the feature. If the same concept doesn't vanish, say you go to a new, more realistic model, you say, oh, I simply cannot find that model, that feature anymore, then you might say, well, it's not really there, it's just an artifact of our modeling. But if I find it something that's close to it, close enough to it in the model, then we can say, well, if the more I find it, the more I think maybe something really is going on according to the theory that we're working with. discussed by a lot of philosophical science, and that's like the last part of the talk. Right? Why did the Ising model ever gain traction? Right. This is a different model where you assume a lattice of different spin, so basically up-down values in the lattice, and you're saying, okay, how does this allow me to model certain electromagnetic phenomena? For instance, when all of them align in the same direction, you get like some special kind of magnet, and otherwise. This, for instance, says that most physicists in the 20s, 30s took this Ising model to be irrelevant to real-world methods, unjustified idealization. Benedict says, by and large, the experimental results back then indicate that the Ising model was inadequate to describe a real ferromagnet. And Yang Chenling says that this is just a mathematical curiosity with no physical relevance. And people who study the Ising model will say it to be contracting the Ising disease.